It's entirely different. Good luck.
Imagine this. You are a professional exercise scientist and a coach. One day, one of your athletes comes to you saying, I want to travel to a high altitude. I hear that this can boost my performance as it can increase my fat oxidation, which will definitely delay my fatigue. As a professional exercise scientist, you basically believe in the experiment. So, you decide to take this athlete into the lab and to test his VO2 max twice. One time at the hypoxia at which the oxygen percentage is reduced, and the other time in the normoxia at which the oxygen percentage is 21%. And based on his VO2 max at each condition, you select two tests that are similar in the relative intensity. So you can start analyzing and comparing the results between both conditions. And guess what? You find that this guy actually got an increase in the fat oxidation despite of the reduction in the oxygen percentage. So you start wondering, is this the case with everyone? So you simply start recruiting more people. And then you notice something that is very weird. Some people are reporting an increase in the fat oxidation relative to the energy expenditure, and some are reporting a decrease. Actually, this story represents the inconsistency of the current literature about the effect of hypoxia on substrate utilization. And that's why our study aimed to investigate the effect of hypoxia on maximum fat oxidation during cycling. My name is Yumna Hassanin. I'm from Hamad bin Khalifa University. Let's start by a very simple question. Why did we decide to study maximum fat oxidation specifically? Simply because it's literally important to everyone, because we consider it as a metabolic health indicator. And indeed, there are many factors that can affect the maximum fat oxidation assessment during exercise, such as cardiorespiratory fitness, diet, equipment that you are using, and many, many other factors. However, the factor that can affect the maximum fat oxidation the most is the intensity. And that's why conditions like hypoxia can affect the maximum fat oxidation, because the hypoxia itself can affect the intensity. There are two main concepts that I would like to introduce for you before going deeper in this presentation. First of all, we assess carbohydrates and fats during exercise using equations, and those equations are depending mainly on the O2 and the CO2. And that's why having a steady state of the VO2 and the VCO2 during the exercise is really important for an accurate measurement, especially that it has been found that the VO2 can be faster than the VCO2. So how can we get this steady state? Simply by a step test. What do you mean by a step test? Step test means that the exercise intensity is increasing but every few minutes. And this is a real example of the step test that we have used in our study. So basically the intensity was increasing every 4 to 8 minutes. And we selected 8 minutes for the higher intensities because physiologically, when the intensity gets harder, the participants require a longer duration to achieve this steady state. The second concept that I would like to introduce for you is the idea of normalizing the intensities. Let's say that you are exercising at 100 watts at the hypoxia. This 100 watts at the hypoxia is going to feel harder compared to exercising at 100 watts in the normoxia, even though it's the same exact absolute intensity. However, if you normalize the intensity, you should actually feel the same in both conditions because you should have similar metabolic stress or similar metabolic disturbance. But the question is, how should we do this normalization? Should we do it based on maximum responses like VO2 max? I'm going to answer this question, but after introducing the exercise intensity domain model, which is a simple model that divides the exercise into mainly three domains. The moderate domain, which ends by the gas exchange threshold, the heavy domain, which ends by the RCP or the respiratory compensation point, and the last domain is the extreme or severe domain, which ends by the end of the exercise. Now let's get back to the question. How should we do this normalization? Should we do it based on maximum responses? The short answer is definitely no. I'll tell you why. Let's say that we have two guys. They are exercising at 60% of their VO2 max. At that case, we are risking that one person might be exercising within the heavy domain, the other might be exercising within the moderate domain. However, if we normalize the intensity based on the exercise prescription model or based on the thresholds, those two guys should feel the same at the same relative intensity. So what do we know about the topic so far? As I have mentioned in the introduction, inconsistent results. And do you know what is common between most of those studies? Using VO2 max as a way to normalize the intensities. And unfortunately, some of those studies do not consider that the participants require longer duration at the heavy domain to achieve that steady state. And that's why our study aimed to investigate the effect of hypoxia on maximum fat oxidation using the exercise intensity prescription model as a way to normalize the intensity. And of course, we selected longer duration for the intensities that put the participants within the heavy domain. And we hypothesized that we are going to have a reduction in the fat oxidation at the hypoxia because it's oxidation and we are basically reducing the oxygen in assembly level. So we basically recruited participants who were healthy, none of them traveled to an altitude the past 3 months, and each of them visited the lab for 4 visits. In 2 of those visits, they had their VO2 max test at each condition, and based on the VO2 max test, we identified their thresholds at each condition, and based on those thresholds, we selected the intensity for the step test. The step test aimed to have 3 stages that place the participants within the moderate domain, and the 3 other stages that place the participants within the heavy domain. And as I have mentioned, we selected longer duration over here to make sure that hopefully the participants achieve the state. In this slide, you can see the VO2 on the y-axis on the left side and the power output on the x-axis. And actually, the black dots represent the normoxia, while the white dots represent the hypoxia. And as you can see, the metabolic rate or the VO2 was almost similar across all of the stages between both of the conditions. And if you notice that the white dots, it's slightly shifted towards the left side compared to the black dots because we reduced the absolute intensity just to normalize the intensity. However, despite of this normalization or reducing the absolute power output, as you can see here, the VO2 as a percent of the gas exchange threshold and RCP was actually similar across all of the stages. The conclusion of this slide is that we were able to successfully select intensities that were well matched in both conditions. And despite of the similar metabolic rate between both of the conditions, the participants got a 25% of reduction in their maximum fat oxidation at the hypoxia compared to the normoxia. And that point was supported by an increase in the blood lactate, reduction in the energy expenditure, while there was no significant differences in terms of the carbohydrates between both conditions. And this might be explained by the fact that the carbohydrates is actually less dependent on oxygen compared to the fats. And I would like to mention that there is a study that reported that there is an increase in the fat oxidation but post-exercise. So it is possible that this increase post-exercise is a compensatory mechanism for the reduction that can happen during the exercise. One of the most interesting findings in our study that we noticed that the maximum fat oxidation was happening a different percentage of the VO2 max. And actually this can make you question whether normalizing using the VO2 max can be considered as an accurate way to normalize the intensity in such studies or no. And it was happening at the same percent in terms of the VO2 as a percent of the gas exchange threshold and the RCP. Lastly, I would like to mention that there was no significant relationship between the gas exchange threshold and the maximum fat oxidation. And this could be explained by the fact that the gas exchange threshold is mainly depending on ventilatory mechanisms, while the maximum fat oxidation is mainly depending on metabolic mechanisms. So in other words, the underlying mechanism between both of them might be a bit different. On the other hand, participants who had a higher VO2 max, regardless of the condition, they had a higher maximum fat oxidation, which is not really surprising. We all know endurance training can lead to many physiological and hormonal adaptations that can increase maximum fat oxidation. So what are the practical implications of our study? Well, based on our findings, we think that maybe using the exercise intensity prescription model can lead to more homogeneous results, even in terms of the substrate utilization. And that's why maybe future researchers can use the exercise prescription model as a way to normalize the intensities and investigate the effect of chronic hypoxia on maximum fat oxidation. I would like to end my presentation by a critical question. Actually, in our study, we noticed a 16% in the VO2 max at the hypoxia compared to the normoxia. Do you think if we had an athlete who stopped training for a while, this athlete, if he or she got a reduction by 16% in his or her VO2 max, is he's gonna have or she's gonna have also a decrease by 25% in the maximum fat oxidation? I personally don't know the answer. Thanks everyone. Thank you, Dr. Nathan and Dr. Juan, my supervisors, and thanks to my colleague Tanya. Thanks everyone.
Thank you, Hamna, for an excellent and very enthusiastic talk. Are there any questions from the public present here?
Thank you very much for your presentation. Very interesting for me. You matched the intensity. I have a question. Did you standardize the diet the days before, or did you have any fasting condition or something like that?
That's a very good question. Yes, actually, all the participants, they had 12 to 8 hours of fasting. That 12 was for those people who came at the morning, and the 8 were for those people who came at night. And actually, the same diet was repeated before each step test, just to get consistent results. Thanks for your question.
Any other questions? So, already late in the afternoon, no questions. Means that you did a great presentation, but I maybe have one question. Did you, because in the beginning of your presentation you spoke about oxygenation, like local responses measurements. Did you include that in this experiment or not?
Yes, actually we assessed the oxygenation and deoxygenation of the blood using the mirrors. However, we didn't have the time to work on the analysis of this yet.
Okay. I think it will be interesting as well to compare like some general with some local responses. And then maybe another question, do you already have an idea, just a hypothesis about the underlying mechanisms of the impact of the hypoxia on this different substrate utilization?
Yes, actually, there are studies that shows that there is a direct effect of the hypoxia on the endothelial function. So maybe if it can increase the diameter, this can make it up for the oxygen, which can affect the substrate utilization. Honestly, the topic is a bit complicated, and unfortunately, there are no much studies that investigated that. But hopefully, we can answer this question with more clear answer in the future. Thank you.
Yeah. Well, thank you very much for an excellent speech.